Lesson 2.6, Combinations of Functions and Composite Functions. In the first part of 2.6, we'll focus on combinations. We're going to look at adding, subtracting, multiplying, and dividing different types of functions. Now, arithmetic combinations of functions just breaks down the definition for sum, difference, product, and quotients of two or more different functions. The sum of a function, or the sum of combinations of functions, is written as f plus g and then x. So do you see how it's the f plus g in the first parenthesis and then x in the second parenthesis? Literally what that means is you're going to take the two original functions and simply add them together. So we'll write just add. Difference obviously would be the answer when you subtract. And the difference of functions is going to be f minus g of x. This means there's a couple things here. First, order matters. Whatever variable is first in the parenthesis is the function that you write first. And then if you're subtracting that second parenthesis, you're going to want to watch your subtraction, because that second parenthesis may have more than one part, and you'll want to make sure to subtract out all of that. So addition and subtraction so far, pretty straightforward. The next one is product. And notice it says f times g of x. And notice, you guys, it's not f times g times x. What this means is the first function being multiplied by the second function. So you may have to distribute or FOIL and then combine like terms. And that's finding the product of functions. We end with the one that may or may not have a restriction in the domain. We end with a quotient, and that's f divided by g of x. Notice that's f of x divided by g of x. And if you have a function in the denominator, remember, you may have to watch your domain or check it for restrictions. So we're going to say check for restrictions in the domain. So literally adding, subtracting, multiplying, and dividing. Let's try a couple of examples. It says given f of x equals 2x plus 1 and g of x equals x squared plus 2x minus 1. The first thing we're asked to do is to find f plus g of x. Then evaluate the sum when x equals 3. So if we're asked to evaluate f plus g of x, using the definition up above, that simply means f of x plus g of x. So we're going to take what they equal and add them together. F of x is 2x plus 1. That's that first function. And we're going to add g of x, which is x squared plus 2x minus 1. If we put this in standard form, the biggest term is that x squared. That's our quadratic term. It has no other like terms with it, so that will go first. And then we have our linear 2x and another 2x, which is plus 4x. And then we have our constant plus 1 and minus 1. They cancel out. Our answer then to f plus g of x is x squared plus 4x. That's the first part of our answer. But it says evaluate when x equals 3. So when x equals 3, we would have 3 squared plus 4 times 3. Well, 3 squared is 9, plus 4 times 3 is 12, and that would give us a total of 21. So to evaluate when x equals 3, we get an output of 21. On the right, we're asked to find f minus g of x. So now we're asked to find the difference. Then evaluate when x equals 2. All right, so I'm going to give myself just kind of a division of space here just to make sure that these don't overlap. F minus g of x simply means the first function, f of x, minus the second function, g of x. I don't know what I was doing there. So f of x minus g of x. Well, f of x was 2x plus 1, or is 2x plus 1. Now, if we subtract the entire second polynomial, we need to put that in parentheses to ensure we subtract every term. Now, g of x is x squared plus 2x minus 1. But remember, we're subtracting that. So we need to distribute the negative into all three of those parts. That would give us 2x plus 1 minus x squared minus 2x and then plus 1. Do you see how all the signs changed? Now let's combine like terms. Our lead term is going to be negative x squared, so it has a lead coefficient of negative 1. That term's gone. Our linear terms are now opposite signs, plus 2x and minus 2x. They automatically cancel out. Our constant, plus 1 and plus 1, becomes plus 2. Our answer simplifies then for the difference to be negative x squared plus 2. Then we were asked to evaluate when x equals 2. So when x equals 2, watch your order of operations here. Check this out, everybody. That negative out in front does not apply to the 2 being squared. So order of operations, that's a plus right there. Let's make sure that just seems clearer. Hopefully that will look so. There we go. As we think about order of operations, we're going to actually do the 2 to the second power first and then make it negative. So, oops, not a highlighter though. So 2 squared is 4, but that negative out in front would make it negative 4. Plus 2 would give us an output of negative 2. F minus g of x when x equals 2 has an output of negative 2. That was addition and subtraction. Let's now move on to products and quotients. We have new functions for f of x and g of x. It says given f of x equals x squared and g of x equals x minus 3, find f times g of x. Then evaluate the product when x equals 4. If we want to evaluate f times g of x, that literally is just the product for each quotient, or for each part in this polynomial. So f of x just times g of x. And remember, up above we said we're either going to have to FOIL or distribute to find products. If f of x equals x squared and g of x is x minus 3, not minus 2, wow, x minus 3, we want the right term in there. Since we have that x squared on the outside, we're going to distribute. That means we're going to distribute the x squared to the first term and the second term. X squared times x would give us x cubed, or x to the third power. And then it's a minus. X squared times 3 is 3x squared. There are no like terms, so this literally is the product. Okay, fine. It says then evaluate when x equals 4. So I'm just going to put this over here. When x equals 4, we would end up with 4 cubed minus 3 times 4 squared. 4 cubed is 4 times 4 times 4, and that equals 64. Minus, be careful with order of operations here. We would have to do the 4 squared before we multiply by 3. 4 squared is 16. 3 times 16 is 48. And that would make this answer, 64 minus 48, equal to 16. So we first found the product f times g of x, and then we evaluated when x is equal to 4. Our final mathematical operation will be division. And once again, we have two different functions for f of x and g of x. It says given f of x equals x plus 3 and g of x equals the square root of x, find f divided by g of x and state the domain. With fractions, we'll likely have a domain restriction in the denominator. Then evaluate the quotient when x equals positive 9 and negative 9. So we have two parts to evaluate for this problem. First, let's use our definition. If we have f divided by g of x, notice we're not multiplying all of that together. The f divided by g part simply means we take the first function, the function in the numerator, divided by the function in the denominator. Ooh, let's rewrite that. Sorry about that. All right, g of x. There we go. So we literally just write it as a fraction initially. F of x equals x plus 3, and g of x is equal to the square root of x. Now, as is, that fraction doesn't simplify. The x on the top does not cancel the x on the bottom. But we have to take a look at the restriction that'll happen because of the denominator. Notice in the denominator we have a rational function and we have an even root. So there's going to be two parts when we figure out our restriction here. So in the denominator, we know that it can't equal 0. We also know that square roots can't be negative. So our radicand, which is x, we would say our radicand has to be greater than or equal to 0, but because it can't equal 0 for the rational, we just say that it has to be greater than 0. It can't have the equal part. So not equal to. Because that would give us 0 in the denominator, and that doesn't work for rational functions. So just be careful when you're stating the domain. This is the answer you want. X is greater than 0 for this particular problem. All right, so we have our function answer, or x plus 3 over square root x. That's f divided by g of x. All right, now you're asked to evaluate when x equals 9. We literally plug it in the numerator and the denominator and then simplify. The numerator is 9 plus 3. The denominator is the square root of 9. Now the 9's don't cancel, but let's combine like terms if possible. 9 plus 3 equals 12 on top. On the bottom, the square root of 9 is a perfect square. It equals positive 3. 12 divided by 3 simplifies to a final quotient of 4. That would be our final answer when x equals positive 9. But watch what happens when we try to plug in negative 9. Still plug it in as normal, negative 9 plus 3 in the numerator, and then the square root of negative 9 in the denominator. In the numerator, negative 9 plus 3 would be negative 6, but in the denominator, the square root of negative 9 isn't possible. It doesn't reach or it doesn't match our description for the restriction in the domain. It's not greater than 0. Since the denominator is not possible, there is no solution when x equals negative 9. So that might happen when you evaluate functions on your homework assignment. And that's our lesson for the first part of 2.6.